Let's take a look at population growth in terms of differential equations. So what we want to look at here, we want to look at how does the rate of population change over time. Now, a general assumption is often made that population growth is proportional to the number of people in the population, meaning the larger the population, the greater the rate of change of growth is. So if we want to look at how do we affect the population, well, if larger population means a greater rate of change of population, we would then need to multiply this by some constant, say k. Okay, so this is a standard assumption about population growth. Now do note, this is sort of works for like population that's growing steadily. Obviously, there are other limitations, right? Like if you look at people on Earth, it's not true that simply this can grow without bound. You have more and more people, trillions, quadrillions, undecillions. No, we have a limitation of resources. We would need a different differential equation. And you're given different differential equations in BC, but in this one is sort of the standard starting point used in AB. Now, let's solve it. Okay, the question is, how do we solve it? We use separation of variables. And we say dp over p, and we get the k could go either, just leave the k here, equals k dt. Okay, so we've separated our variables. Now we take the integral of both sides. Okay, we're solving for population here. And what we get the natural log of p equals, now k is just a constant, so it goes out, it's just dt, so it's k dt. Sorry, kt. And you've got this plus c, right? You've got to have a constant here. Now, since we want to know an equation for population, this is actually fine, but we're going to do a little more with this. Let's go ahead first and solve for p. So how do we do that? We take e to both sides. Okay, so if you take e to both sides, in effect you're putting like an e here and an e here, and e would be to the whole thing, right? And then what do we end up with? We end up with the population equals, now we've got this e to the kt, but that's really then, it's kt plus c, but that's like times, let's separate out the constant. That's times an e to the c. E to the c is like its own constant, and so we say that population equals some constant a times e to the kt. Okay? And a, furthermore, okay, we can solve this by setting time equals to 0. Okay? What happens if we set time equal to 0? Okay? Well, if time's equal to 0, we get sort of like p of 0 here equals a, e to the 0 is 1. So why do I put p of 0? Because it's when t is 0. It's the initial population. And so we can actually better write this as p equals p naught, the initial population, times e to the kt. And so, this is really cool, I think. If you assume that the rate of change of population, the derivative, is proportional to the population, you get this equation, which has exponential growth, right? The e is exponential growth, okay? You ended up with a natural logarithm, right? It came through this equation. So that is how you derive the equation. The equation is here at the end. And basically, in a lot of the calculus problems that you might be given, you just use it, okay? You might be given like the initial population and then like some particular case in time. And so you might have to like work with the equation a couple of times to finish it out and get the results, okay? But if you start with this equation, it could be that you're not necessarily doing calculus to actually solve the population problem. You're actually using a calculus result. And that actually does happen in the kind of standard AP calculus curriculum. So what I want to do is something a little more interesting. Okay, so this is from a text, Ordinary Differential Equations, by Morris Tenenbaum and Harry Pollard. And they provide a nice introduction at the beginning, which is a real story. And so in this story, some boys are with a dog. The dog goes down a hole and doesn't come back. So the boys go down into the hole and they discover a cave. And the cave has like paintings on the walls, and it has remnants of charcoal from a fire. So here's the question. Can we as a society figure out when people were in that cave by determining by looking at the charcoal, right? And so how would you do this? Okay, so charcoal is dead wood, and all living organisms have two carbon isotopes, C14 and C12, and one of them, I forget which one, decays over time, and one is stable. And so if we know the properties of carbon, okay, we can maybe figure out when people were in that cave using differential equations. So what might this look like? Okay, in this particular case, one of the carbon isotopes is radioactive. And what that means is the amount of carbon will decrease over time. Now, if it decreases over time, this differential equation changes. It becomes dp dt equals negative kp, right? And, it can be nice just to get a little extra practice, and instead of trying to manipulate it from here, let's just solve this differential equation and see how it's different. Okay, so we get dp over p equals negative k dt, and then we're going to integrate both sides. Same thing, then we get natural log. It's pretty much the same thing. Natural log of p equals negative kt. And, it's right, the k is going to be negative. Everything else is the same. You take e to both sides, take e to both sides, plus c. If you take e to both sides, you get population, they cancel, equals e to the negative kt times e to the c, that's a, which is p naught. So it's times p naught, e to the negative kt. Okay, so what you would need then is you need information specific to the problem at hand. Okay, that is what I am going to look up in the text and provide for you. Okay, so this is a real example in history in 1940, and it's really cool because you can use these equations, okay, we're doing math here, we're doing equations, to figure out when people were in a cave. Okay, like how far back in time, using charcoal being consistently radioactive, and assuming that this equation holds. Now, it might not be perfect, but it's thought to be pretty darn close. Okay, so what do you get? What you find out is the following. You find out that, and it looks like C14 is the isotope, that after 10 years, okay, I'll write this down. So, if specificity, let's say 10 years, and then you get, what does it say? 99.876 remains, okay? 99.876. And so this would be the charcoal, so it's the C14 remains. Okay, so what we need to do then is sort of put this into the equation, okay? And so clearly, the E, right, we're going to have e to the negative k10, or e to the negative 10k. And what we're trying to figure out here is we're trying to figure out k. And simply put, okay, we have this p naught here, and look, if 99.876 of it remains, that's what you have here. You have 99.876. Excuse me, it's a percentage, right? So you'd have a decimal point there, right? 99.76%, okay? Percent, and so when you put that as a decimal, it's 0.99876 p naught. Right? Because that's how much remains of the original. Okay, so we can solve this, right? This is a pre-calculus problem. The p naughts cancel. You take the natural log of both sides. You get ln of 0.99876 on the left. Now on the right, if you take the natural log, the negative 10k just comes down. So it would just be k divided by negative 10. Okay, and that would then give us the solution of k equals 0.30, so 0.000124. Okay, so we have taken something that's known. Okay, in 10 years, 99.876 of C14 remains. This is like for trees. Okay, I'm not a chemistry person, so you have to bear with me in some of the finer details. But we now have an equation with the k in. Okay. So we now have, let's shift it up here, we now have the equation P equals P naught times e to the negative 0.000124. And then that's times t. Okay, so we went back here to sort of plug in the value that we found. And this is sort of like a standard, by the way, type of problem that you would actually see. This one's a little bit cooler because of the result. Okay, so we're almost there, but we need more information. And so what would have to happen is somebody would have to come in and look at what those kids found, look at the charcoal that remains, and figure out how much C14 is left. Okay? And when somebody did that, they found that 85.5% was gone. Okay, so 85.5% of C14 was gone. And so what that means then is, right, 14.5 is left. So once again, we can do just like we did here, right? It's 0.145 of the original. Now P naught is sort of for population. P could be any variable. I mean, in this case, you know, you could use another variable because it's not, I mean, it's not population. You could use A, you could use anything. You know, you could still use P for like, it's not standard though to use P for the amount of carbon. Okay, and then so this equals the original amount, e to the negative 0.00124t. And once again, the p naughts cancel. We have a differential equation that we can solve, and it's simply whatever the ln of 0.145 over this, right? Natural log is going to be the same thing. I mean, the variables are flipped, but you have something times another variable. The natural log and the e's cancel, so you divide by the negative 0.00124 to get the t in time. And you also have to know your units for time. And we've been talking about years, okay? So this is kind of built in that we've been doing this in terms of years. So this will reveal, okay, let me be clear about this. This is going to reveal the amount of time that has passed since the tree was cut down. Okay, so a tree's cut down. There's this cave, and they build a fire in it, okay? What we're trying to figure out is when did that happen? When did they cut the tree and build the fire? Okay, charcoal remained, right? These kids found it. And what you get is T is 15,573. Okay, so what this does is it verifies that there were civilized people who had cave paintings and fires over 15,000 years ago, right? I love this example. I remembered reading it the first time, which is why I brought it to attention here in these videos. This is the power and beauty of this stuff, because it's not just like mathematical sort of trickery. It is designed to model real life, right? And when it's done well, you can use these tools to actually figure things out about life. And this is where you kind of end up with discrepancies, or where you have in the past between what scientists will say about how old things are and what you might read in other kinds of texts that aren't scientific based. So this is kind of the style of argument that's often presented when we look at things like the age of the earth. Now, this problem is not about the age of the earth, but this problem is about the age of human civilizations. Like, if you assume dp over dt equals negative kp, and these facts about carbon-14 are true with trees, then yes, there were civilized people for sure here 15,000 years ago. So that's for me, it's like the beauty and power of differential equations. It's really what you get out of them. And I will also add in conclusion that differential equations were enormous, in the pre-computer era, because before the rise of computers, how did you figure things out about the world scientifically? A lot of it was solving differential equations. You sometimes have to keep like different solutions to different types of differential equations in your head. And there's still a lot of value in differential equations. They're studied intensely by math and science majors, but it doesn't hold the same kind of weight that it used to, because if one has to solve a differential equation for science and you need to know some kind of numbers, you can use computers to approximate the solutions to differential equations. In conclusion, let's take a look at one final example. So we talked about this F equals ma. And what about a spring? So a spring has a restoring force. What we would say is that the force, it's a negative proportion. So it's like negative kx, okay? Because you pull out the spring and it goes in the opposite direction back. Now, how would we solve this in terms of a differential equation? Okay, so we know ma then is negative kx. And so if we want to we can write that down. We have ma equals negative kx. And we can write the a in terms of a differential equation, right? So we've got a is d squared x dt squared. And now we have that equals negative k over m times x, okay? So this is a differential equation. Now you might think, okay, we can solve this using separation of variables, but sometimes you can solve these by inspection. And what I mean by that is, can you think of a function? Now this is what our x is here, okay, because it's motion, so x is going to be some function that basically you take two derivatives, you kind of get back to where you started because it's x, but it's negative and it's times something. So how do you get, if we break it down, what if it was just negative x, okay? Can you think of a function whose second derivative is the negative of the original, okay? Sine goes to cosine, cosine goes back to negative sine, right? And same thing with cosine. Cosine is negative sine, sine is negative cosine, okay? So sine and cosine work. But now what about the km, okay? Chain rule, okay? Now if you do it once, it would just be sine, whatever, km times theta, or times t for time. But when you do it twice, okay, how do you get this from taking two chain rules? What's the square root of that? Okay, so by inspection, this becomes x equals, now it's going to be, cosine I can tell you is commonly used with springs because instead of starting with 0, you start like at a point outward. And so we can write this as cosine of, and then if it was just t, that would go to the negative, but we need the square root of k over m t. And that is the solution, although I should say it's the solution within a parameter because, note that it doesn't matter. You could have a plus something else, right? Because that's not going to actually affect it. So you could have plus some other constant like beta or something. Okay, so that is the solution to this differential equation. Okay, kind of cool. And by the way, I'll also say that sometimes this is written as x equals cosine of omega t. And then, for angles, they sometimes do it more like this. Fancy Greek symbols. And is that a psi? And then here in this case, then obviously W would equal root K over M. So I just wanted to show you one more example of, a differential equation that's solvable by inspection. Okay, it's uncommon to solve them by inspection, but this is really cool. This is a big equation. It's harmonic motion. Okay, harmonic motion, and what happens when you release the spring? It goes back and forth, right? Which is why it's like a cosine. So it kind of adds up. All right. So I hope you enjoyed that. Has some population growth, a real example of radio decay, in this case using charcoal and the isotope carbon-14, and then another bonus one here, which is solving the spring equation for simple harmonic motion using Newton's laws.